Welcome, ladies and gentlemen. Let's take a look at our trapezoidal approximation for our space shuttle Endeavour. Given this velocity versus time data, we know the definite integral in general represents a product between the dependent variable values, in this case velocity, and the independent variable velocities, in this case time. And so if my velocity is in feet per second multiplied by seconds, the resulting products would give me feet. And that's great news because I want to estimate the altitude above the surface of the Earth after this full 125 seconds, or just over 2 minutes. All right, in order to do that, I'm going to set up my trapezoidal approximation. And because my subintervals, 0 to 10 seconds, 10 to 15, 15 to 20, 20 to 32, because those are not of equal width, I can't use a single delta x over 2 in my trapezoidal setup and then parentheses times the function values. I have to do an individual trapezoid for each subinterval. No problem. I know that that's given by 1/2 times the width of the subinterval times the sum of the bases, right? In this case, 0 and 185. Plus, I know the next subinterval, 1/2 times the length of the subinterval, 5 seconds, times the sum of the bases, 185 plus 319 feet per second, plus 1/2 the width of the third subinterval appears to be 5 again, times the sum of the bases, 319 plus 447. And so on and so forth. And so where do we get interesting? Well, still 12. Not too interesting. Uh-oh. Writing's hard. 742. And, 27. And I feel like we're closer here, but still not there. So 27, 59, 62 is just 3 seconds. And the moment we've all been waiting for, I guess that's right, the last one, full 63 seconds until solid rocket booster separation. That's 63. 1445. Awesome. Go ahead and raise your hand if you had this set up. So 1/2 for each of them, sum of the bases times the height. Great. And now we'll go ahead and get our answer. Dun, 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 dun. Brendan?
219,167.5 feet.
And you said what point?
5.
Awesome. Let's keep 3 places. Everybody keep 3.
It's 25.
Oh, yeah. I know label on there. Speak. Emily?
So I did the left Riemann sum and the right Riemann sum and divided it by 2. When is it better to use the trapezoidal compared to the other one?
It's just a time issue. So, did you get this answer?
Yeah.
Good. So the trapezoidal approximation is the average of the right RAM, right, the right-hand sums and the left-hand sums. It's just a question of which one is quicker for you. And so, if the subintervals are of equal length, I would say the trapezoidal approximation is quicker. If they're unequal length, you guys still have to enter each of these twice anyhow, 1325 and 1525. So then it probably doesn't matter. You see what I'm saying? So if these had been equal, then we could use the single formula, a single trapezoidal thing, you know what I mean, with the 1/2 delta x out front. But it probably doesn't matter. Awesome. What questions do you guys have about our area approximations? Great. So today we're going to move from our approximating the area underneath the curve to getting the exact area underneath the curve algebraically using pencil and paper methods. Yes, that's right. We're going to develop the fundamental theorem of calculus and apply it. We're going to do both parts today because that's how we roll in BCEO, right? We're going to look at both parts today, and then you're going to have a chance to practice. But first, we've got to take care of some housekeeping. So I'm going to pause the recording, and then we're going to pass back tests. Okay, ladies and gentlemen. So we saw last class with our area approximations that we could get an approximation for the area between the function and the x-axis by using rectangles, right? And when we ever to use a rectangle for that area approximation, it's called a Riemann sum. And so, in this Riemann sum, what does the n represent? And for this, right, I just want you to think. You don't have this here. We're going to get the definite interval definition in just a minute. But I want you to think back to our rectangles from last class. What does n represent here, right? What does n represent when you do this approximation, Sophia?
The number of terms.
Absolutely. So the number of intervals, the number of rectangles. So that's the number of rectangles. What does the sigma tell you, Danny?
To sum it all
Yeah, you're going to be summing. What does the f of c sub k, careful Riley, times delta x sub k represent? Well, that product right there is the area of one typical rectangle. So that's the area of one rectangle. And if that's the area of one rectangle, whose height is given by the function value, f of c sub k. So that's the height of that rectangle. And delta x sub k, that would then be the width of that rectangle. Then, as those widths, right, of my rectangle shrink to 0, I can fit more and more rectangles into, right, that space, which will leave me with the exact area underneath the curve. So if I let that, the width of each subinterval shrink towards 0, I can fit more and more rectangles into the space, fill it up exactly, and I'd be left with the exact area in between the function and the x-axis. So that will give me the exact area. Between my function f and the x-axis. All right, so what I want to do is go ahead and use this. This was from your OTL number 1 from last time. We used a Riemann sum to estimate the area underneath the graph f of x equals x squared plus 1 on the interval 0 to 4. So I provided this one on your note sheet. Let's go ahead and just partition her so we can see visually here. From 0 up until 1, 2, 3, 4. So we were talking about finding, right? We were talking about finding the area in between my function f and the x-axis over that interval 0 to 4. And the directions from your OTL asked us to use the midpoint rule with 4, right? With 4 equal subintervals. So I can always get my delta x by taking the length of my interval, b minus a, and dividing it into the number of intervals subintervals I'm going to use, or rectangles in this case. So b minus a would be 4 minus 0 all over 4. So it looks like each subinterval is going to be 1. That means each rectangle is going to be width 1. No problem. And I'm going to use the m. What? I'm going to use the middle of each subinterval in order to generate the height for each rectangle in the approximation. So where am I going to look on the first subinterval to get the height? I'm going to look right in between at 0.5. I'll use that to generate my rectangle height. 1.5. I'll use that to generate my rectangle height. 2.5. And so on and so forth. All right. So let's go ahead and well, I better write it down. We'll go ahead and do delta x times, and I'm using the midpoint of each subinterval to generate the height of my rectangle. I'll just use my function notation f of and the values, and then I won't have to actually write down each decimal separately. I'll go to my calculator one time and do my eval. So let's go ahead and do our delta x is given by 1/2 times the sum of my rectangle function value. Because I have equal subintervals, I can just use that 1/2 delta x first. And I'll do f of my first rectangle height comes from when x is, right, 1/2. Plus my next rectangle height comes from when x is 1.5. Yes? Plus my next rectangle height comes from when x is 2.5. 1, 2, 3, 4. Plus my final rectangle height comes from when x is 3.5. Yes? No? Danny?
Why are we multiplying by 1/2?
Oh, sorry, by 1 the whole time. the width of my subinterval. I'm thinking half. We're multiplying by the width of my subinterval is 1 the whole time. That's my delta x. I was saying that. I said delta x, and I put 1/2. Okay. So delta x is the width of my subinterval that we calculated is 1. That's the width of each rectangle. Thank you very much. It should be 1 the whole time. Thank you, Danny and company. All right. So then let's go ahead and do that. I'm going to go to my calculator one time. And on my calculator, I'll simply enter 1 times, and I'm going to do f of. So I already have my calculator. Uh-oh. That's not going to work unless I do x squared plus 1. And now I can use, and not have to do my decimal or table and write them down or worry about copiers. I'll just do bars, y bars, function, and I'll do 0.5. And I'll do 1.5. And I'll do 2.5. And 3.5. I almost made it. What do we do? So what did you guys get?
25.
You guys got 25? Hey, that's great. So what does 25 represent? 25 represents an approximation for the area underneath the curve and the x-axis on my interval 1 to 4. Well, I could get a better and better approximation by continuing to use more and more rectangles. I could use the left-hand side, I could use the right-hand side, but it turned out I'd still just have approximations. And so if I want to get the exact area, that's when I'm letting the width of each subinterval go from 1 to 1/2 to 1/4 to 1/10 to, right? If I let the width of each subinterval shrink to 0, then I'm going to fill up the entire space with rectangles, and I'll be left with the exact area of the curve. So as I let delta x go to 0, the number of rectangles does what? Goes to infinity. Do you guys have this one then? I can put this one on? Yeah. So my number of rectangles goes to infinity as delta x, the width of each subinterval shrinks to 0. A in my definite integral represents the left endpoint of my interval. B then represents my right endpoint of my interval. That's an x value, if I'm integrating with respect to x. F of x dx still represents, that product still represents the area of a single infinitely thin rectangle. Where f of x gives me its height of that infinitely thin rectangle, and the dx gives me the infinitely thin width, right, of each rectangle. All right, so now I have the definition of the definite integral. So the definition of the definite integral, right, is the limit as n goes to infinity, that's the number of rectangles going to infinity, of the sum of the individual rectangle areas, right, starting with k equals 1 and going up to n, of that product, where my product is f of c sub k, a typical x value anywhere in my subinterval, multiplied by the width of that typical rectangle, call it delta x sub k. And if I sum up all of the areas of those infinitely thin rectangles, I would be left with what? Well, I would be left with the exact area in between the function and the x-axis on the interval a to b. Now here, we're limiting our discussion for the moment for positive functions, right? Positive functions, f of x. the exact area. We saw last year that if the function was beneath the x-axis, right, then that area had to be interpreted as an opposite, right, an opposite contribution to the overall value of the definite integral. We could just take the opposite of it if we wanted to get total area, but we'll save that for next time. All right, so now let's remember the numerical approximation command on our graphing calculator. Bless you. Math 9, comma baby, my favorite calculator command, one of the 4 that we have to be able to use on the AP exam. Math 9 to numerically get a definite integral. And so let's everybody practice with that, and we want to see how well our 25 did. So we're going to use the same function and use our grapher to approximate the exact area under the curve, still using f of x as x squared plus 1 on the interval 0 to 4. So let's go ahead and do that with our grapher. I'm going to Math 9 it. And I've got pretty print up here, right? A lot of you are, nobody's really using the 83s that much. If you have the 83s, then you'll do expression, comma, x, comma, a, comma, b. So for us, our a is 0, and our b is 4, and our f is y1, and our variable is x. How do we do? How's our 25? Pretty darn close, actually. I'm impressed because we went 4 units and it was a squaring, so it's growing pretty quickly. So I'm actually pretty impressed. Is this exact? Well, no. 25.333333 is not exact, but if I math bracket will give me exact. It's trying to tell me 76 thirds, yes? Trying to tell me 76 thirds. So the question now becomes, how is it that we could get that 76 thirds exactly and algebraically? And that's where the fundamental theorem of calculus comes in. So to develop that conceptually today, we're going to first define a new function called an area accumulator function. That is, as we start at the left-hand side, now that we know that a definite integral represents the area between a function and the x-axis over an interval a to b, if we start here at x equals a and we scan, right, towards the upper limit. In this case, we'll let that equal x. If x were 1, we'd be scanning from a up until, x equals 2. If we started here at an arbitrary a and we scan up until x equals 2, then the value of the definite integral would give that shaded region. But what if we let that upper limit vary and be 2.5? Well, then we'd be scanning and accumulating, continuing to accumulate area up until 2.5. Or if I let it be 3 1/4. Then we'd be continuing to scan from a up until 3 1/4 and accumulating area. Do we see that this itself is a function because it takes on different values depending upon what we let that upper limit x equal? Let's go ahead and use our grapher now to just quick change the limits, and we're going to generate f at 1, f at 2, f at 3, f at 4, and f at 5 and compare. So what we're doing is we're going to let f be my area accumulator function starting at a. In this case, we're going to let a equals 1, and we're going to scan up until x, but we're going to let x be my independent variable. So you guys didn't have this, but you're going to put it right on your thing. So we're going to let a equal 1, and we're going to scan up until my independent variable value x is 1. On my grapher, I'm scanning from, can I do that? No. Do I have to do this every time? No. How's that? So let's go from 1 to 1. And let's do our function was, let's do this function is y equals square root of x minus 1. So let's do the square root of x minus 1 as my function, and let's accumulate area. Are we good? Kind of? So everybody, we're going to enter y equals square root of x minus 1 and have this picture. Yeah, so that's what we're doing. And we're going to scan from my lower limit 1 up until my upper limit. In the first case, I'm letting x equal 1. So how much area is accumulated from 1 to 1? 0 units. I'm getting 0 units. How much area is accumulated from from 1 to, what did I say, 2? 2? .6666687. Will that mean? Nope. Alright, that's why we need to put it on the calculator. Alright, so what do we got here? Are we good? So what do we get for f of 3? 1.886. F of 4, 3.464. F of 5, 5.333. Alright, go ahead and take a look at our values for f, the area accumulator function that starts at my lower limit a and scans from left to right, and as it does so, right, gives a numerical approximation for the area shaded in green. Raise your hand if you were able to generate the same values for f. Did you get the same values? You did? Okay, so we're easy cheesy with the calculator evaluation. What I want to do now is point out how my values of f, this area accumulator function, vary, right, as I let my upper limit change. Itself is a function. Well, how are f and f, what? How are f and f, little f, and big F related? Well, we know that the derivative of big F is little f. Therefore, the antiderivative of little f is big F. So f is an antiderivative of f of x, and the indefinite integral of f with respect to x is big F of x. Please note, indefinite integral and antiderivative are synonymous. And so an antiderivative is synonymous with an indefinite integral. And we know that the derivative of big F equals little f. This means the derivative of f is f. So f prime of x equals f of x, and that's going to open up all kinds of doors for us. So if f is any antiderivative of f, then the integral from a to x of f of t dt, we could have used f of m dm or f of p dp, f of t dt is given by big F of x, and then plus some constant. As you know, we could have had some constant added to my antiderivative expression that would disappear when differentiating. So if f prime equals f of x, there's some constant that could have been there, and we'll account for that with a plus c. And by choosing my x to equal a, we gain a very interesting result. So this is what I want to point out today that's different from our AB discussion last year in our generation of the Fundamental Theorem of Calculus. So if we let this x up here, if we choose that to equal a, watch what happens. So our integral from a to a of f of t equals big F at a plus c. And interpreting the, sorry, I need PT there. Interpreting this as an area accumulator. Anything that's a 9? I am. Anything that's an A? Yes? By interpreting little f, or sorry, big F as an area accumulator, how much area is accumulated as I scan from A to A? 0, comma baby. And so this left-hand side equals 0. And why? Are you sensing that tremor in Mr. Fritz's voice? Why is Mr. Fritz getting so excited? Well, because watch what happens. What must this arbitrary constant be when I let that upper limit x equal a? Well, that arbitrary constant c must be given by what? Negative f at a. If I were to solve this for c, then c equals negative f at a. And look at this. I get the integral from a to x of f of t dt equals big F at x minus big F at a. Now you should be recognizing this from AB, right? As I go to evaluate that definite integral of little f on the interval a to x, I'm generating the antiderivative big F evaluated at my upper limit minus the antiderivative function big F evaluated at the lower limit. This should be familiar because now if we choose my constant, my limits of integration to be constant, then we have a means for evaluating definite integrals exactly and algebraically using antiderivatives, exclamation point, hooray, and I need balloons, but they don't sound when we're recording anyhow, so I can add them. We've got the Fundamental Theorem of Calculus, the evaluation part. And so let's go ahead and write that. The integral from a to b of my function f of x dx, the definition was a limit of Riemann sums. Now we have a means for evaluating it, and that's called the evaluation theorem. What do? I find an antiderivative function, call it big F, evaluate that upper limit, evaluate the lower limit, and subtract them. And so I find my antiderivative function, big F, any antiderivative function will do, evaluate my upper limit b, and evaluate my lower limit a, and then subtract the two. This is a big deal. All right, this is a big deal. I now have an algebraic way to analytically evaluate a definite integral, and by golly, we can generate that 76/3, I sure hope. Furthermore, differentiation leads to the other part of the Fundamental Theorem of Calculus. And I told you it was a big day, we can do double, right? We can do double duty. If I'm going to differentiate the integral from a to x of f of t dt, recall that this part in green, we've already seen was big F of x minus big F of a, and I now can differentiate term by term. What's the derivative with respect to x of big F of x? Well, the derivative of big F of x gets me right back where I started to little f of x. Minus, what's the derivative of big F at a? Well, a is just a constant. So f at a is also a constant. And what's the derivative of any constant? 0. Oh my goodness. The derivative of my area accumulator function, right? The derivative of big F of x is little f of x. Is that shocking? No, because we knew that big F was an antiderivative of little f, and we knew that because the derivative of big F is little f of x, and yet it still is earth-shattering. Why? Because the Fundamental Theorem of Calculus Part 2, the antiderivative part, solidifies differentiation and anti-differentiation as inverse processes, just like multiplication undoes division, and addition undoes subtraction, right? So too, differentiation undoes integration, and this is huge. And so now we've got both parts. The Fundamental Theorem of Calculus antiderivative part says that the derivative of this integral expression, right, regardless of what independent variable or dummy variable is used in my integrand function, is simply the integrand function evaluated at x with that independent variable now replaced. And so this is huge. The derivative of an integral expression is the integrand function evaluated at my independent variable. This is a big deal. So I made a sheet that had both of them on there, and I've been getting there a roundabout way, but I'm hopeful that you were able to get the two in there at the right time. So let's go ahead and use the Fundamental Theorem of Calculus, the evaluation part now, to see if we can do what our calculator did before, but better. So here we're going to find the exact area underneath f of x equals x squared plus 1 on the interval 0 to 4. How do we do that? Well, we're looking for this 1, 2, 3, 4. We're looking for the area of the shaded region. And we know the area of that shaded region is given by the integral from left-hand limit 0 up until 4 of x squared plus 1 is my integrand function with respect to x. And we have a means for evaluating that. If we can find an antiderivative function, any antiderivative function will do, but I'm going to choose the one with c equals 0 because it's less terms, for x squared plus 1, evaluate the upper limit, evaluate the lower limit, and subtract the two, then I'll get the exact result. So I'm going to find an antiderivative function for x squared plus 1. In other words, what differentiates to x squared plus 1? Well, how about 1/3 x cubed plus x? Will this differentiate to x squared plus 1? Well, yeah, using your knowledge of derivatives, you know this would be 3 times a third is 1, x to the 1 less is x squared, plus the derivative of x is 1, and I can evaluate that from 0 to 4. Let's do it. So I'll plug in the first one, all the way through, 1/3, 4 cubed, I should like this, plus 4 minus, and then 0 all the way through, equals, what's that, 64 thirds, plus 4 is 12 thirds, and square root of the inverse tangent of pi. I'm getting that, what do we want, 76? Are we getting 76? I sure hope we are. How does that compare to our math track before? Superbly. It's the same thing. Right? So now we have a means for evaluating a definite integral exactly and algebraically, and we're not going to do samples of these because you, right, are going to do that in your OTL. So lots of your OTL is practice, and I did select odd exercises so you can check your answers. Okay, so what's trickier? Well, we've got our printables, and now we're going to go ahead and apply the antiderivative part. So if we're given, right, g of x, which is that area accumulator function, where my lower limit is a constant, then regardless of what that constant is, because the derivative of a constant is 0, I know that the derivative of the area accumulator function, that is g prime of x, is given by my integrand function evaluated at my upper limit, my independent variable, in this case, x. And so if g is given by the integral from constant to x of f of t with respect to t, then g prime of x is f of x. It doesn't matter, right, what dummy variable is used in my integrand function. When I find that antiderivative and evaluate my upper limit, x, and the constant a, then that variable, the dummy variable t or p, right, no longer is a part of my expression, and when I differentiate with respect to x, an x function, I'll have x's in it. And so if g of n is given by the integral from c, some constant, to independent variable m, of f of p with respect to p, then the derivative of g, that is g prime of n, equals what? Radio? Frequency modulation? Yep. F of m. FM, AM, FM. That's serious. You guys are serious anyhow. Oh gosh. Let's do it. Is negative pi a constant? Yes, then the derivative, right, of the integral expression is the integrand function evaluated at the upper limit. This equals cosine of x. It's that easy. Is 0 a constant? Yes, it is. Then the derivative of that integral expression is the integrand function, with the important distinction that we've evaluated at my upper limit. Do you guys want to do the long way ones to see? Are you okay with the short way? Right, the long way, if I could find the antiderivative function, and I could, it would be inverse tangent, and evaluate the upper would be inverse tangent of x minus inverse tangent of 0, right, is 0. Then I would differentiate the inverse tangent of x. What does the inverse tangent of x differentiate to? It's like, so simple, it's cool. All right, what happens then? What's the tricky part? And what's the tricky part of your assignment? Well, when my limits, right, aren't plain Jane x, right, when it's a composite function, now I can go ahead and apply the chain rule to my differentiation. So if g is given as an area accumulator, that's an integral expression from constant up until now a composite function, instead of just x, some function of x like 2x or x squared or h of x, call it in general, then the derivative of that expression is still my integrand evaluated at my upper limit, and then times the derivative of my upper limit in accordance with the chain rule. That is, the derivative of a composite function is the derivative of the overall function evaluated at the inner, and then times the derivative of the inner. In this case, my inner function is that upper limit, which is the self function of x, call it h of x. So what would I write for this? Well, the derivative g prime of x will then be given by my integrand function evaluated at my upper limit, in this case h of x, and then times the derivative of my upper limit. So I just need to multiply by the derivative of that upper limit. That's the only difference. What does that do for us? It means we can now evaluate expressions like this. So if g is given by the integral from -2 to sine of x of blah, then I'll simply evaluate my blah at my upper limit and then multiply by the derivative of my upper limit. So long as that bound is a constant, right? We've got to have a constant. So I know that this is simply 3 minus sine squared x, and then times what? Cosine x. That's it. I could write that as 3 cosine x minus sine squared x cosine x if I wanted to, or I could leave it like this. Go ahead and do example 4 with your partner. Be ready to share. So what did you guys get for 4? All right, what did you guys get for 4? Courtney and Marissa?
Cosine of x squared.
Raise your hand if you had the same thing. Cosine of x squared times 2x or 2x cosine x squared. Good job, you guys. Uh-oh. Is my lower limit a constant? No, but I could certainly rewrite this and make the lower limit a constant. Recall that I can switch the limits. That is the order of my scan, right? By taking the opposite of my definite integral. And so if y is given by the integral from x to 5 of an integrand function, I could rewrite that as the opposite of the integral from 5 to x. Remember, this switched the directions of my scan, and now in the sense of rectangles, instead of scanning from left to right with stepping over a positive delta x widths, right? I'm scanning from right to left, stepping over with negative delta x widths, and that's what the negative sign does to counteract that. So what are we going to do? Simply flip the limits and put a negative, and proceed as normal. So I'm now going to get negative, and then lower limit's a constant, evaluate my integrand function at the upper limit. That's it. Awesome. Anything tricky? Yes. When my limit, when I don't have a constant, right? When I don't have a constant, what do? Well, now I can simply do my evaluation theorem combined with the differentiation. What? Antiderivative evaluated at the upper limit minus antiderivative evaluated at the lower limit. And when I take the derivative now, right, there's no that constant in between, right? That it would drop out before. Now I just have the derivative of that second part. It's a subtraction. Keep in mind you could always break this up at any constant in between, call it a, right? And do your evaluation with the 0 as a subtraction. In any case, we're going to use the evaluation theorem when combined with the chain rule. So I'm going to get the integrand function evaluated at my upper limit times the derivative of the upper limit minus the integrand function evaluated at the lower limit times the derivative of the lower limit. So let's go ahead and see what that looks like. I get 1 over 2 plus e to the what? X squared times the derivative of the upper limit, 2x, minus the integrand function evaluated at my lower limit, e to the 2x, times the derivative of my lower limit, 2. So it's simply the evaluation theorem combined with the chain rule. Can I make this look prettier? Yeah, I hope so. 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. Those denominators are not the same, right? And so I can't combine them to a single fraction. But that's the last part of the first block in your second set of pages. So you'll be able to handle that stuff now. Awesome. I feel like you guys did great today. Go ahead and share your response for not the definition of the definite integral, but rather the fundamental theorem of calculus. So yes, this is the limit as n goes to infinity of the sum of my product, right? For the area of the rectangles, but I want the fundamental theorem of calculus evaluation part and antiderivative part for today's closing. All right, so what's the evaluation theorem say for number one? Grace?
Big F of B minus big F of
Raise your hand if you get the same as Grace. Big F of B minus big F of A. Yes! And the antiderivative part of the fundamental theorem of calculus says that what? What did you get for that? Kobe?
Equals f of x.
And what kind of F? Big or little?
Little.
Little F of X. Raise your hand if you get the same as Kobe. That's right too! Guys are killing it, but I didn't have enough pages. In fact, I had to take out 2 in order to get you on 1, so we have to write this down. Ready? Right here. That's what we're adding. So we're going to include, I'm going to pause the recording